All right, TINs, or triangulated irregular network partitions, are really interesting because they are sort of a hybrid between vector and raster data, which we're about to talk about in a little bit. But essentially, TINs are triangles, right? They're triangles, and they are irregularly shaped triangles. So they're made up of points, and then you just connect the points together in the smallest triangle that you possibly can, and you end up with something like this. And it's a very efficient way of representing surfaces. And so they're used to store and display surface models because, again, they're just made up of these points, really, and then the lines connecting the points. Okay, so this is an interesting way to represent surfaces. It's a series of these polygons, and you see them very often when you're dealing with, for example, LiDAR data, where you've got millions of points in the point cloud, and you can create a tin or this surface by connecting all those different points with planes. And I do all sorts of work with that in remote sensing and some other things. But let's just sort of wrap up again what vector data are. Vector data, it's points, lines, polygons. They're perfect. You keep on zooming in on vector data. It will keep being, if you look at a vector line, it'll keep being this beautiful sharp line. They work great for discrete features with well-defined locations and shapes. But if you are dealing with spatial phenomenon that vary continuously over space, like temperature or precipitation or rolling topography, things like this, vector data are not the way to go. And the way to go is what we're about to talk about next. Rasters. Okay, raster is the way to go. So in a raster model, space is defined as this array of equally sized cells. And each cell contains an attribute value and location coordinates. And so over here, this is a continuous elevation raster. Okay, so this is made up of, if we zoomed in here, eventually it would become pixelated. We'd see individual boxes, and each of those boxes would have some kind of a value, and the value would represent elevation. Over here, the boxes, the individual pixels, actually represent a land cover class. Okay, so lake, agriculture, residential, road. Okay, this is still a raster. If you take a photo with your point and shoot camera or your iPhone camera and you zoom, that's a raster. Okay, an important difference between a vector and a raster is that raster coordinates are contained in the ordering of the matrix itself. What that means is, if you know the coordinates of the corners and you know how many columns and how many rows there are, simply this is, raster cell 1, 2, 3, 4. You can get the coordinates of any of these particular guys because the coordinates are born out of the ordering of the matrix. Unlike those points we were showing, which the point had an individual coordinate system, right? The coordinates in the raster are just sort of inherent in, what position they hold inside the cell array. And we'll see some examples of that in a second if that's a little confusing. This is an example of a raster data set. So this is a data set I collected from Isle Royale National Park up in Lake Superior in the mainland. And this is an elevation raster. The colors are elevation, and then superimposed on that I've got this transparent hillshade relief model. So, this elevation changes over space, and to express that with a vector would be terrible, but to do it with an image with a raster, it makes a lot more sense to do it that way. And I use this is a Leica ScanStation C10 terrestrial scanning LiDAR unit. Okay, so we got a raster data model, and then this is vector data, right? These are individual points, and we can actually convey the information which is held in these points in a raster way by saying, okay, let's say in this cell, how many points are there? These points could be anything. I don't know what they are. They could be people, they could be trees, they could be anything. There's one, right? There's one. In this cell over here, how many points are there? There's 3. In this cell, there's 0, and so on. And we can represent the number, the count in here by some kind of a color, right? And so 12, which is a very dense amount of points, this is represented by this very dark color. And 0, right, is represented by a very light color. This is a very efficient way of holding on to and storing data. but you've lost something, right? You've lost the specific locations about where these individual point locations are found. And if your question requires that you know exactly, where these guys are in relationship to one another, then raster's no good for you. But if you don't care, or depending on and if you had a finer raster, right? If the cells were much more tight in here, and instead of being from here to here, they were, more grid lines, you could get finer and finer and finer. But I guess part of it just depends on, what do you need the data for and what are you thinking about. If this is fine enough resolution for what you're doing, then hallelujah, right? But if it's not, maybe you still need to live in this vector world. These are some representations of points, lines, and polygons on both the vector side, right? We can keep on zooming in. It's going to be the nice clear line. And the raster world, right? Where things are pixelated. In remote sensing, we can look at sensors which are sensitive across the electromagnetic spectrum, and for each wavelength we can have an individual raster. What we're looking at here is what's known as a data cube, and this data, this layer up here is in the red, and this guy down here is in the infrared, and so on. And then we can just sort of blow this out, and we can get a spectral signature. So this is an applied example of rasters, but in a remote sensing kind of sense. If we have rasters which are georeferenced, the columns correspond to the x-coordinates in the east-west direction, and the rows correspond to the north-south coordinates. The origin is, by definition, typically in the upper left corner, and this is a example. So let's say we've got some kind of elevation raster that's got 463 rows, so 1, 2, 3, 4, all the way down to 463. 318 columns, 1, 2, 3, all the way out to 318 columns. And each cell is 30 meters, right? So from here to here, 30 meters, right? From here to here, 30 meters. So 30 meters by 30 meters. And if we are given the x and y coordinates at the lower left corner, and we're given the x and y coordinates at the upper right corner, we can do some tricky math, and we can, verify that the rows and column numbers are correct, right? Because the number of total rows is this number, right, minus this number, and the number of total columns is this number minus this number. And we know that each one of these guys is 30 meters by 30 meters. And so if we do that, this is the total number of, this is the meters, right? So this is saying that at 519.1065, which is over here, right, is the number of rows. So this is row up here. Oh, what happened to my mouse? This is row 519.1065, and then down, if we kept going down to the end. This would be row 5177175. The difference between those guys divided by 30, which is the cell size, would give us 463, and there are 463 rows. We're happy. We can also figure some things out if we know the coordinates of these guys. We could figure out what the coordinates should be in the center, right? Because it's going to be halfway down. These are some examples of some rasters, right? So this is a topo map. You see this guy all the time. This is a elevation map, right? This is actually from Mars. This is a raster image. This is an oblique aerial image which was collected over the campus, right? All of these guys are rasters. Rainfall Atlas of Hawaii, raster. Okay, so raster is wonderful, vector is wonderful, but each has its own place. In this last short little bit, I'm going to talk about bringing in tabular data into ArcMap. It's not really important where this data set came from, but what is important about it is it's got information and it's got columns for northing and easting. This is where metadata comes in. This particular data set the coordinates are in UTM zone 16 north. This is a map projection, okay? Universal Transverse Mercator zone 16 north. So we know what these units are. They're in meters, and we know what they correspond to. They actually correspond to Isle Royal and Lake Superior. Okay? So we've got a table which has in the table northing and easting location data. You can bring that directly into ArcMap and turn it into points. And the way you do that is a little non-intuitive, so that's why I want to talk about this. You would go to File in ArcMap, add data, add XY data. And if you do that, you need to make some choices about which column corresponds to the X and which column corresponds to the Y. But once you do that, you can bring that data in, and it's beautiful, and you can populate your arc map with points. So if you've got data like that, that's the way to do it. And that should pretty much be the end of this video tutorial. And if it's an Excel spreadsheet, you might have to choose which actual sheet you're talking about. All right, very good.